to define what's called a derivative, which is instantaneous rate of change, we need limits to do it. So that's why we did all the limits. Except they squeeze in one more section, number one, before you do derivatives. Limits at infinity. You want to make sure you know how to find limits at infinity. We've already done a couple of those, right? Limits to infinity, like just, you know, like a problem where we said, what's the limit as this went towards infinity? Well, we got to cover everything. We got to hit every type of scenario when x is going towards infinity. So, hey, a few things I'm just going to put on board just for algebraic review. This is the first thing. This comes up in my intermediate algebra class. The absolute value of x squared, or in another way, not only the absolute value of x squared, the square root of x squared. All right? I'll just leave it up here. What's the square root of x squared? X, right? Just x. The real definition is this. It's absolute value of x. And so, a lot of times, you know, we just go square root of x squared, you're right, is x. But in this particular section, we're going to really use that to our advantage. We're going to want to know the absolute value of x squared, square root of x squared, excuse me, is actually the absolute value of x, which is a piecewise function, isn't it? So I'm going to go even further. Define this without the bars. Ooh, good. It's an x or it's a negative x. Now, when is it x? If x is doing something, when is it negative x?
When x is positive.
And I'll just put an equal to one of these. Will that work? I'll put it there and I'll put it there. So there you go. So I'll just leave that up there. Just because there were a couple problems you'll notice in this section, 2.6. I can tell you which one. Number 23, number 24, have radicals in them. And that's why we're going to want that. I think you'll find it useful. I brought up the overhead because some of you remember, can't you find limits graphically? So never forget that. It's like, well, if this thing's so weird looking, it's kind of abstruse, a little difficult to understand, I will put it on my calculator and look at the graph. So that's why I put that there. So that's that. Is there anything else? Well, I think we should just put down one limit as x goes to infinity. How about this guy? The function 1 over x. You know what that graph looks like? Plug in a 1, what do you get? 1. Plug in a 2, what do you get? Half. Plug in a 10, you get 1/10. The numbers keep getting what? Smaller. So this graph, everyone, just kind of keeps going down and down and down and down and down, but it approaches a horizontal asymptote. Just like that. And you probably can tell. Do you know what the limit as x approaches infinity of this expression is? 0. It's going to 0. You can see it numerically or graphically. So that's why I wanted to leave that up there. We can leave that up all class. 1 over x, it's going to 0. By the way, this graph, there's something going on over here. I should show it. It's over here like this. So this graph, everyone, if this is the y-axis, this is the x-axis. This graph actually has a horizontal asymptote and a vertical asymptote. This thing has a horizontal asymptote at y goes to 0. It's actually got a vertical asymptote. Let's label it here. Your vertical asymptote is the equation x equals 0. But the limit as x goes towards infinity of 1 over x is 0. Just knowing that numerically or graphically really helps us out. Cool. So let's start with concentrating on rational functions. That's where I want to start today. Rational functions. And once we know how to make these graphs, then we should find it easy to make the limits. And this is just a, 5-10 minute review on how do you graph rational functions. Because if we can make the graph, then we can find a limit. Finding limits graphically is not hard if we know what the graph looks like. So there's basically 3 main scenarios with rational functions. Rational function is just a function defined as a over b, where b is not equal to 0. All right, so one example would be this. Y equal to 2 over x minus 3. now I want us to make the graph. So we're just going to do a little graph review. We'll do 3 scenarios. So I want to look at this graph, or when this thing has a VA and an HA. It's got a vertical asymptote, but it also has a horizontal asymptote. How do you find the vertical asymptotes of rational functions? Brilliant! He knows, that was great. They said, look, he goes, look at the denominator, set it equal to 0, you know exactly what the vertical asymptote is. Right here, I want to give you your VA. So it's at x equal to 3, right? I'm going to go over here, 1, 2, 3, and just. I can use this chalk for the asymptotes. Here. Right there at 3. All right, now how do you get the HA? Well, there's a few scenarios. If it's rational, everyone, that means there's a polynomial up here and a polynomial down here. A simple way to do it is, if your higher exponent or power is in the bottom, it's 0. So what's the exponent of that 1 right there? 1. What's the exponent in the numerator? 0. It's an x to a 0. So where's the highest exponent located? In the denominator. And if your highest exponent is in the denominator, then yes, this HA is always for a rational function right there on the x-axis. So don't worry, we'll do another scenario. You go, well, what if it isn't on the bottom? But on this, it's just an easy way to make a graph, and now you got to plot a couple points. We'll get the graph going. Here, just make a little table. What would be 2 easy points to plug in? How about 4? We could get a point over here, and then what's a point on this side of 3? 0? I'm just picking 2 easy points to plug into the graph and make a sketch. Cool? All right, what's 2 over 4 minus 3? 2. All right. Everyone, I know half the graph. There it goes. There's that graph. But notice it's flattening out. You and I are going to look at limits as x goes to infinity. Well, if we can see this, we know where it's going, that's going to give us our answer. Now, what's going on at 0? Negative 2/3. It's like right there, because there's the origin, everyone. There's the y-axis, there's the origin. So it's a little bit lower than it, but this graph is on this side, is now going to, see, it curves towards these asymptotes. There it goes. Your calculator makes these too. But hey, why is knowing these graphs so helpful in this section? Why do I start 2.6 with this? Because they're going to ask you to find the limit as x approaches infinity of something like 2 over x minus 3. Well, can you see it? It's just going to be the horizontal asymptote, what I call the horass. It's just going to be the horass of it, right? Which is just what? 0. Find your horizontal asymptote. You'll find your limit as x goes to infinity of a rational function, right? He goes, that for all rational functions? Well, there's one scenario we got to be careful of, is when there no horizontal asymptote doesn't exist, and it has a slant asymptote, and we'll talk about that. All right, so there's one scenario, and that's the scenario if the highest power is where? Located in denominator. So then we're like, okay, we got it. So we put a big wall. We're like, well, what if the powers are the same? So how about y equals 2x plus 3 over x minus 1. Well, where's the VA now? 1. And you and I will talk about the HA.
2.
Oh, I heard it, it's 2. How did you do that? That was good.
Yeah, because as at numerator and denominator has the equal number.
Exactly. Victor, brilliant. That was awesome. Evan, do you notice the highest power in the numerator is a 1? The highest power in the denominator is a 1. They're matching. So if you're curious, like, how do you find a horizontal asymptote? If the highest powers in each part are the same, it's the coefficient, or the ratio of the coefficients. You go, really? Always. If it's a rational function, polynomial over polynomial, like this. Absolutely. And what's so great about this? Because when you do your limit to infinity, it's the horass, right? So that's why it's so helpful to know that. this HA is y equals 2. Well, we'll make the sketch, but when we gotta find the limit as x goes toward infinity, we know where it's going. Alright, so here, I just think it's good to make these graphs so we can really see it. Seeing math helps. Alright, right here, there's a vertical. And then there's a horizontal at y equals 2. So the graph is going to flatten out there. Let's get a couple points going. Okay. How about x equals 2 and x equals 0? I do either side of the vert S. What's going on at 2? 7. What's going on at 0? -3. 2 got up to 1, 2, 3, 4, 5, 6, 7. Way up here. Well, there it is. See it? And this graph's just going to go, and then just right towards infinity. And over here, it's going to go through that point and ride towards the S horizontal asymptote of y equals 2. So this HA, here's the HA right here. Y equals 2. And there's the VA. So I'm going to write it down. What's the limit as x approaches infinity of the rational expression 2x plus 3 over x minus 1? It's just what? 2. Graph. Our knowledge of horizontal asymptotes. In fact, check this out. What's the limit as x goes to negative? Over there. 0. It's the same, isn't it? It's the word. Same thing over here. What's the limit as x goes to a negative infinity? It's a 2. It's not negative 2. It's the same. It's also 2. They're both 2s. So let me get this a negative. Sorry. Negative infinity. As x approaches negative infinity or positive infinity, the limit of this rational expression is the rational function will be 2. So those are 2 easy ways. Please use that to your advantage when you're dealing with rational functions. But there's one other scenario. We did highest power in the bottom. We did powers are the same. What's the other one? Yeah, what if the highest power is on top? So just something like this. How about y equals x squared over x plus 1? I mean, something just as simple as that. That's a rational function. F of x equals x squared, but the highest power is on the top. Well, let's do this. VA. HA. Well, let me just get to this one. It doesn't have one. It has a slant. And when it doesn't have a horizontal asymptote, it has a slant asymptote when the highest power is on top. So now we're noticed that this process of finding the limit doesn't work so well. But there's another easy way to deal with this one, so we'll be good. All right, where's the vertical asymptote? -1. All right. It's over here.
I have a question.
Sure.
Can we like divide the numerator by the denominator to find the slant edge?
Brilliant. You want to do it?
Yeah.
Let's do it. And when I'm going to do it, I don't know if you knew this. There's a way to find this slant asymptote. We're going to go in here, and we're going to do long division. Now, if you're like going, oh gosh, that's a pain, we'll do it. But I do want to point out you don't have to do it to find the answer. All right, but I think it's a good idea so we can see what the graph would look like. So when I'm going to find this slant asymptote, and you go, how do you do it? Well, we have to do something called long division. What's that? Well, we put this like this. Put this over here, and then you got to go like this. I'll hide the 1. X times what is x squared? X. Then you multiply this x to both of these and you put it right here. So you get x times x is what? X squared. X times a 1 is a x. And you subtract down. Usually by now I have students like in calc class, they're like, oh my gosh, this is a pain. You can find the limit without doing this, so we'll talk about that. Now, do I add or subtract down? subtract, that's a 0. These cancel, but 0 minus x gives me negative x. Now you ask yourself the same question. Hide the 1. X times what is negative x? Negative 1. Now when you just found the equation with the slant asymptote. It's right there. I'm going to go back and finish this out. Distribute, multiply that negative 1 to both of these. You get what? Negative 1 times x? Negative 1 times a 1. But this is just a remainder. When you subtract down here, see that minus 1? This will just be a remainder. So these go out. But 0, remember there's a 0 here. 0 minus negative 1 is just, that's your remainder. It doesn't affect the slant asymptote. That number right there. So don't think you need that number. It's right here. This is the equation of your slant asymptote if you want to do it. It's right there. Y equal to x minus 1 is the slant asymptote, which is a line that does what? It went right through here and it goes, the slope is 1 and it just keeps going up by 1, right? Rise 1, run 1. Rise 1, run. It's just a straight line. But I thought it'd be good. I thought it was a great idea we did this because we can get a sense, we can make the graph now. The graph's going to either be like in here, it might be over here, maybe over here. We just got to plot 2 points. So let's get 2 points. Everyone, little table? How about plug in 0? What's 0 with 0 plus 1? 0. So when I got part of this graph, it goes right to the origin. Remember it bends towards these asymptotes? Here it is. It's like a Nike swoosh. There it goes. But you know what? I know the limit as x approaches.